Hi, I am Aditya Mathur.
Hi, I'm Neil Stippenhauer.
Together, we will take you through a short tour of our secure water treatment test bed, also known as SWaT. SWaT has a physical part, which I will focus on.
And a cyber part that I will focus on.
Okay, let's go. Validation of techniques for cyber defense often requires a realistic environment. While mathematical proofs and simulations are valuable mechanisms for validation, demonstrations on test beds are often convincing and bring the much needed realism. It is with this belief that iTrust has embarked upon the design and construction of test beds to support research in the design of secure public infrastructure. In this short video, my colleague Professor Neil Stippenhauer and I will take you through SWaT, Secure Water Treatment Testbed. Designed and built by teams of professionals, SWaT is a goldmine for conducting experiments to understand the impact of cyber attacks on a modern water treatment plant, assessment of techniques for cyber defense, and the generation of new ideas. SWaT produces 5 gallons per minute of pristine water filtered using modern membrane-based processes of ultrafiltration and reverse osmosis. It contains a 6-stage distributed control system. It supports both wired and wireless communications. Thus, SWaT is perhaps the most modern testbed for research in the design of secure cyber-physical systems. Let us now take a tour of the testbed. We are now at stage 1 of SWaT, also known as raw water processing stage. This is the control station for this stage. It contains dual Allen-Bradley PLCs. One PLC serves as the primary and the other as backup that immediately takes over when the primary fails. Each of the 6 control stations in SWaT is configured with a dual PLC configuration. The purpose of the controller at stage 1 is to manage the flow of raw water from the inlet to stage 2. Water flows into tank T101 when the motorized valve located behind the tank is opened. Water flows out of the tank to stage 2 when this constant speed pump is turned on. Tank 101 is marked with 4 level indicators: HH, H, L, and LL. These visual indicators correspond to numerical values of water level in T101 and are used by the PLC to control the valve and the pump. All tanks in SWaT carry the same level markings. The level sensor is an ultrasonic level sensor. The water level is transformed into a 4 to 20 milliampere value that is finally digitized to indicate to the PLC the water level in the tank. All tanks are fitted with an ultrasonic level sensor. These are 2 sensors to measure the pH and oxidation reduction potential of the raw water. The measurements are transmitted to the PLC in stage 2. We are now at stage 2 of SWaT, the chemical dosing or the pre-treatment stage. The controller in stage 2 is responsible for adding an appropriate amount of 3 chemicals to the water: hydrochloric acid, HCl, sodium chloride, NaCl, and sodium hypochlorite, NaOCl, for disinfection and pH and ORP balancing. These 3 sets of dual dosing pumps are controlled by the PLC at stage 2. This is stage 3, the ultrafiltration stage. The PLC at this stage turns this pump on to move water from tank 301 through this UF or ultrafiltration unit to tank T401. The ultrafiltration unit contains a large number of micrometer membranes to remove solid matter from incoming water. This stage contains several motorized valves to control the flow of water into and out of the ultrafiltration unit, as well as sensors to measure pressure values. For example, this is a differential pressure meter to measure the pressure drop across the ultrafiltration unit. This pressure drop is used to decide when to initiate the cleaning cycle for the unit. In addition, there are several other flow and pressure meters to monitor properties of water going in and coming out of the ultrafiltration unit. The filtered water is held in tank 401 that serves as a feed tank for the reverse osmosis unit. Stage 4 is meant for dechlorination of water before it is moved through the reverse osmosis units. This is done to prevent oxidation of membranes in the RO unit. The PLC controls the ultraviolet dechlorination unit to remove free chlorine from the water from tank 401. The controller may also use sodium bisulfate, that is NaHSO3. Dechlorination is necessary to remove free chlorine before water is fed into the reverse osmosis unit. The ORP, which is oxidation reduction potential, the ORP monitor is used to measure the absence of chlorine. The dechlorination process reduces free chlorine to harmless chlorides and readies the water for feed to the RO unit. Stage 5 controls a variable speed pump to feed water through a two-stage reverse osmosis unit labeled RO501, RO502, and RO503. This stage is by far the most complex of all stages in SWaT in terms of programming and physical design. The complexity arises due to the sensitivity of the nanometer membranes in the reverse osmosis unit to free chlorine and to any solid particles. Permeate from the RO unit is sent to tank 601 and the reject to tank 602. The permeate is recycled into the raw water tank. The reject is used to clean the ultrafiltration unit. Stage 5 contains several sensors and protection devices. There are flow meters, ORP and pH meters, motorized valves, and a cartridge filter. Stage 6 controls the cleaning of ultrafiltration unit through a process known as backwash. The PLC is programmed to initiate a brief cleaning cycle every 30 minutes. A backwash cycle can also be initiated when the differential pressure across the ultrafiltration unit exceeds a pre-programmed value. Water from the reject tank in stage 5 is used in the cleaning cycle. The water so used is drained.
Okay, so I'm going to talk about the networking and control side of SWaT in a little bit more detail. In general, we have two network components or network sections in SWaT. We have what we call the level 1 network and the level 0 network. The level 1 network contains the historian and SCADA server, and in addition it contains the STAR topology, which connects all the PLCs in SWaT. SWaT consists of 6 main process stages. Each process stage has its own main PLC device and a backup PLC device. All these PLCs are connected together through this level 1 network STAR topology. In addition, each process stage and each PLC is connected to local sensors and actuators through a level 0 network. This level 0 network is also Ethernet based, and it connects the PLCs in particular. In most of the cases, the PLC is connected to a remote I/O unit, which is going to do the conversion to analog signals to the sensors and actuators. In both the level 1 and the level 0 network, the industrial Ethernet IP protocol is used for communication. This industrial protocol is in particular used by Allen Bradley products. Although the name is Ethernet IP, it's not directly related to Ethernet or IP. Instead, it's running on top of TCP. It's an application layer protocol that allows to exchange measured sensor data, to send commands to the actuators, to reconfigure the logic of the switches, of the PLCs, and in addition to update firmwares and to similar more complex actions on the network. So this protocol is being used both in level 1 and level 0 network. The level 1 network contains, of course, the SCADA workstation, the historian, and also the HMI. These will periodically query all the PLCs for current data of the sensors and also send new control actions if required. So we're going to have a look now at the central switch that we're using to connect to SWaT topology. This central switch has 24 ports and it connects all the PLCs, and it also allows us to essentially get a copy of all the exchange traffic through several mirroring ports. So the central switch is housed in our rack together with a set of servers we're using to house our virtual machines and some analysis software. So in total currently we have 4 hardware servers here which are running a larger number of virtual machines, and in addition we have the central switch here. Currently we only have one 24-port switch. You see here all the gray cables are essentially connections coming directly from the PLCs. So the PLCs are using the switch to communicate with each other. In addition, we have the SCADA and the SCADA workstation and the storing connected to this. The HMI is connected to this as well, and we have then 4 ports which are essentially providing a copy of all the network traffic that is being exchanged for later analysis. So this copy of the traffic is fed into the other servers, and on these servers we have a number of virtual machines running that are running intrusion detection software, for example. We also have external collaborators. For example, this company here is setting up its own intrusion detection system to analyze the traffic that is exchanged in the plant in real time. So this was the level 1 network. Now we'll have a look at the level 0 network. Each process stage has its own cabinet which houses the main PLC and the backup PLC. The PLCs are of course connected to the level 1 network through a wired Ethernet, and in addition there's a second network, the level 0 network, in this cabinet which connects, essentially it's a ring topology, Ethernet ring, which connects the PLCs with each other in redundant fashion, and in addition it connects it with the remote I/O unit and other components which are also able to talk Ethernet IP. So in this case here, the PLCs don't directly have I/O units, so they can't receive analog signals or send digital signals or send analog signals. To communicate with the sensors and actuators, the PLC will send messages over the layer 0 ring to the remote I/O, and the remote I/O is then translating into analog signals. In both the level 1 and the level 0 network, we mainly use wired network connectivity. We are always able to switch into a wireless connectivity mode by essentially flipping a switch which is provided on the casing. So if we enable the wireless communication here, we will automatically disable the wired connections, and in this case we would have both switched to level 0 network to wireless communication and the level 1 network of this PLC to wireless communication. So now currently the PLCs are communicating with the remote I/O over a wireless link, and they're communicating with other PLCs over a wireless link as well. So now we can have a look at the one example sensor. So this is a flow meter, for example here. This flow meter is measuring, of course, the flow of water through this pipe. The flow meter itself is an analog component, so you see there's 2 cables coming into the housing here. It receives power, of course, and in addition it provides a current-based analog signal. So this current-based analog signal is between 4 and 20 milliamps, and this current-based signal is essentially now fed through this cable all the way to the housing, and in the housing it will be converted by the remote I/O unit into a digital unit, and this digital unit is then supplied to the PLC, and the PLC is basing its control decision based on this value, and in addition the PLC will report this value to the historian and the SCADA system. That was a brief overview of the networking in SWaT.